welcome to another great video. And then we have another Newton's second law problem. In this case, we are given this diagram that you see here. So this is from, I think, Gauteng 2023. And then I can just go and check it out online. So now, this problem, we have a 2 kilogram block, wooden block. It's resting, or it's on a metal surface that is inclined at 30 degrees. So this is the wooden block. Okay, and then it's connected by a frictionless pulley to a 5 kilogram mass, which is hanging vertically. The system is free to move. That's a key hint right there. So, I mean, if you use your, not even, can I say, common sense, right, you can say that 5 kilogram is greater than 2 kilogram. Right, before we even consider any other physical or physics phenomena, we know that this is heavier than that. So 5 kilograms is heavier than 2 kilograms. So it's likely to pull this thing such that it moves up and therefore ultimately coming down this side. But obviously we are not considering the fact that there is friction here, which might stop all of that and make it impossible, right? But they did say the system is free to move, so that's just what it means. Now, what else do we have? The coefficient of kinetic friction. So when they say kinetic friction, that is another hint. It basically means the system is moving actually. If it is moving, we know for a fact that it's moving downwards when we look at it from the 5 kilogram box's perspective, but it's moving upwards like this when we look at it from the perspective of the 2 kilogram block, right? Of course, in physics, we don't say perspective. I'm just using it so that you get the gist of what we're saying. We usually say reference, right? So when we look at it from the 2 kilogram block's reference frame, we can say, well, it's moving upwards this metal surface. And then we look at it from the reference frame of the 5 kilogram block, it's moving downwards. Right, so we're given the coefficient of this metal frame between the wooden block and the metal plane, as 0.3. Well, it has no units, obviously, because it's the coefficient of kinetic friction. Now, before we do anything, what I always advise is just draw the free body diagrams, or you don't even have to draw them yet. You just annotate your diagram and then you can draw them on the side. So let's first start by annotating our diagram. Right, so we have this diagram here. So let's start by just annotating our diagram. Right, so now we know that weight always acts downwards. So just pull down for this one. Weight always acts just straight down, vertical. Then we have weight. Then we have normal force. Normal force is always perpendicular to the surface. So it's going to be perpendicular there. Normal. Then this thing will have the tension due to the string. And then it will have a frictional force pulling it, resisting the motion. So that's our kinetic frictional force. Then when we come to the 5 kilogram block, it'll just have its weight and this, the tension T. So this tension is equal along the spring. The string. So it's the same everywhere along this string. Okay, so it's the same for the 5 kilogram block. It's the same for the 2 kilogram block. That's what happens with the tension. Why is it doing that? Okay, that's weird. Okay, so from here we can take out our free body diagrams, or also remember this 30 degrees here. You can simply take it and put it there. 30 degrees. Right, so now we can have our free body diagrams for these two objects. For the 2 kg block, we have something like this. With our tension, we have our normal force. Okay. We have our kinetic friction. And then we have our weight going straight down. Going down. That's our weight. This is for the 2 kilogram block, right? We can annotate it. This is just on your separate piece of paper, so you haven't even started answering the questions. Then this is for our 5 kilogram block. This one is simple. It just has 2 forces in it, which is our tension T and then the weight of the block, W. So these are our 2 free body diagrams. So now we can start answering the questions, or caring about whatever the questions are saying anyway. So now the first question that we are asked is, define the term kinetic friction, right? So kinetic friction is essentially, if you remember, we said it only exists once an object is moving and it's in motion, or it's sliding against a surface, or 2 surfaces are moving relative to one another, right? So they rub against each other, and that's why we have kinetic friction. So that's the reason why we do not care about static friction when objects are moving. It's because of the nature of how kinetic friction is created to begin with. So now, what the definition says, for at least in the recommended definition, is that kinetic friction is the force, basically it's the force acting parallel to a surface, right? And then it opposes the motion of a moving object relative to that surface. That's the usual definition that we use, right? Or the recommended definition, to ensure that you get this full 2 marks. Okay, so let's write it. We say it's the force acting, okay, force so this is how you would write the definition. So you have a force acting parallel to a surface and opposes the motion of a moving object relative to that surface. Okay, so that's how you define kinetic friction. Now for 3.2, we are asked to draw a labeled free body diagram showing all the forces acting on the 2 kilogram wooden block. Okay, we can just call this 3.2 then. So where we started by first annotating our given problem, the diagram that is given in our problem. Let's see. Okay, so we can call that 3.2. This is 3.2 basically. Let's use that's our 3.2. Okay, so if you check the marks here, it's 4 marks. So that means your free body diagram has to have 4 forces. So 1, 2, 3, 4. We are fine. That means we would have gotten our full 4 marks. Okay. Now we go to 3.3. 3. It says calculate the kinetic friction experienced by the 2 kilogram block. Okay. Luckily, we have already been given the coefficient of kinetic friction. Therefore, we know that whenever we have to find kinetic friction or static friction, we must always know the normal force, right? One way or the other. Okay. So in this case, we must first find our normal force. Right. So I'll copy this diagram and let's put it here. So if you remember, we have an angle here of 30 degrees, right? This means that we will have our weight. We usually call it our weight perpendicular, or there's just the y component of weight. Depends what your teachers recommend. And then this weight will also have an x component. Okay, I made it a bit shorter. Okay, it will also have an x component. I'm using different colors so you can see it. So it will have an x component. We usually call it weight parallel because it's parallel to the x-axis, and weight perpendicular is perpendicular to the x-axis. All right, so now we have these two. Oh, this is also called, depends who teaches you physics, right? But let's use then the most common convention, which is weight parallel and weight perpendicular. So for weight parallel, we then say we have weight parallel is weight, in this case it's sine 30 degrees, while for weight perpendicular, if you remember how we resolve vectors, it's just the same thing. Okay, nothing has changed. You can check our other video where we focused on resolving vectors if you don't understand where we get these coses and sines. Cos 30 degrees. Okay, so this is what it would look like. So now what we then have to do is we are tasked with finding the 3.3, the kinetic friction experienced by the 2 kilogram block. So we know that kinetic friction is nu Fk, kinetic friction is mu times the normal force. We don't know the normal force yet, so we must find it. To find the normal force, we usually take the sum of all the forces along the vertical axis, which is along the n, right? So usually if there's only two forces, which is the normal force and whatever other force usually can be weight, in this case it's weight perpendicular, we just say normal force is equal to that force, which in this case is weight perpendicular. Why? Because whenever we sum these forces, we would have said n plus, saying we choose that side as positive, which is the direction of n, it means the weight perpendicular is going to be negative, and then we say this must be 0. Why? Because the object is moving along the axis where t is located, and it's not moving up or down, it's moving along this axis, which is our new axis. It's not moving along the y, it's moving along the x. So that's why we say it's equal to 0 when we add the normal force and the perpendicular component of the weight. Okay, so what would have happened here is you would then get that n is simply weight perpendicular, because you would have transposed this to that side. So that's where this whole thing comes from. And that's why when you have another force there at the bottom, it ends up being N plus, weight perpendicular plus whatever force. Let's say it was Fy. Right, so that's where it all comes from. It's very important to know that for your own understanding. Okay, and we know that weight perpendicular is weight cos 30. So we can therefore say F K simply mu K times weight cos 30 degrees. Some say, once you practice enough, you'll just say mg cos 30 degrees. Then we can sub in our values. We have 0.3 times m, which is 2 kilograms, times 9.8 times cos 30 degrees. You'll notice that whenever I substitute, I use brackets. They help me so that I don't miss any signs. Right, for instance, if 0.3 was negative, which obviously it would never happen, but I'm just making an example, I would have a negative here. So I can neatly pack my numbers so that I know, okay, this one is negative, this one is positive. That way I never forget signs and so on, and I never mix things up. Okay, it's a matter of convenience, numerical convenience, if I can call it that, or computational convenience. So now we can find our Fk. I get that Fk times is simply 5.09 newtons. Okay, that's my answer. So that's my Fk. Okay, so that's what it would look like. So this is our 3.3. Okay, we're done with 3.3. Okay, I don't know why this. Okay, so for 3.4, we are asked to state Newton's second law. By now, you should know this by heart. You should know it off by heart. So, as always, whenever you have a net force acting on an object, that object will accelerate in the direction of that net force. So, it will accelerate with an acceleration that is directly proportional to the net force, but inversely proportional to the mass of that particular object. So then we end up, that's basically everything you need to say about the Newton's second law. So we can just write it here. And then there are shorter versions of this. Just stick to what your mind can take, and then what also your teachers recommend, because I know teachers give a list of definitions for you to memorize. But if you write it like this, you still get 4 marks in the exam. All the keywords are in this definition, so you are very much fine. So let's go to 3.5. We are now asked to find the acceleration of the system. So now what happens is we know that whenever we are dealing with Newton's second law, right, you have Fnet, which is the net force. Right, this, by the way, is Newton's second law in symbols or in equation form. Right, notice that in this question they specifically asked for it in words. That's why we wrote this whole paragraph there. So they always say in words if they want you to write the statement, but in a rare case they would say in symbols. Then you would have to write it like this. Okay, it probably will never happen though, but in an instance where it happens, you would have to write it like this. Okay, so we are looking for this A. Right, so we have 2 options. We have option 1, where we analyze each block individually, and then we make a subject and solve and so on. Option 2, we take the whole system and then we work with it like that. So let's start with the option 1, which is what most people usually prefer. We'll start with the 2 kilogram block. Let's just start with the 2 kilogram block. But since, let's see. Okay, since we have, let's start with the 2 kilogram block. Because we already did a few calculations for it. Let's say Fnet and I'm choosing its direction of motion as my positive. All right, so it means, what does it mean? My weight parallel will be negative because it's opposite to the direction I chose as positive. It also means my Fk, which is the kinetic friction, will be negative, which is always negative, obviously, because it always opposes the direction of motion. So the only thing that will be positive here is T. T plus minus Fk plus minus my weight parallel. Okay, is equals to my MA. Ooh, nice. So now, if you remember, we did calculate T. Said T was, not T, Fk, which is the kinetic friction, 5.09. Then we'll say the weight parallel is minus mg, which is 2 mg sine, I think. Yes, sine 30. Sine 30. And then this is 2a, because we don't know a, that's what we're looking for. Okay. So from here, we can make T subject. Remember, you make T subject because you are looking for a. If you are looking for T, you would make a the subject. So you make the parameter that you are not looking for, you make it the subject of the formula. And then the one that you are looking for, you don't make it the subject of the formula. It's always like that. So that when you equate the two equations, you can simply solve for that parameter or variable. So now we have T is 2a plus 14.89. But this is not cast in stone. It's not a rule. You could have made a subject of the formula. It's all up to where the calculations lead you. Okay, so there's no rule here for this particular calculation. Right, so now we have this. We call it our equation 1. Why? Because there's two unknowns and we can't solve them with the current equation that we have. So we must find another equation. Remember, if you have one unknown, you can use one equation to solve for it. If you have two unknowns, it means you need two equations. If you have three unknowns, it means you need to have three equations to solve, and so on and so forth. So now we can say for the 5 kilogram block, here we do the same thing. We say, well, we're taking up, no, since it's going down, I'll take down as positive. Notice my positive directions are always where the object is going, not opposite to it. Otherwise it means my friction is positive and so on, and that just confuses me. And also means I must go to my acceleration and add signs. It just makes it algebraically messy. I don't need that. I like a convenient life, especially if I have control. So the direction of motion that is positive is where this thing is going. Therefore, it's Fnet is MA. Now, there's only two forces here. There are only two distinct forces. You have the tension, which is unfortunately going up, so it's negative, plus our weight, which is going down, so it's positive. Then we have MA. Now we substitute we will say minus t plus mg, which is 5 times 9.8, and then 5a. Okay, this means t is simply 5 times 9.8, 49 minus 5a. That's our equation 2. So since we know that t is the same for the 5 kilogram block and the 2 kilogram block, we can just simply equate equation 1 and 2 and solve for a as required by the question. Okay, so we can come this side and say 1 is the same as 2. Equation 1 and equation 2 are equal, which is something you'd also do in maths. So that's why when you're not good with your maths, your physics will also suffer. So you must fix your maths, because your physics is nothing without your maths. Okay, say this was 49, right? 49 plus 5a. From here, it's just all about grouping, and then you divide, and then you find your answer. So what we can do, okay, so I think we forgot a sign here. And then, okay, this is 49. Yes, we did forget a sign. This is negative. Okay, so now we just manipulate the equation such that a's are on one side and the other numbers are on the other side. So we can just plus 5a here, plus 5a there. Then you'd have 7a plus 14.89. This is simple maths, guys. Then you transpose this. So that means you have 7a equals to, I get 34. From here, you just divide by 7. Then that's your a. I get 4.87 meters per square second. So that's our acceleration, right? So of this entire system, okay? And then there's obviously method 2, where so with method 2, if you remember in our other video, you basically ignore the interface. I call it an interface, but it's this string that connects these two blocks. And what you end up doing is you create one big block which has both masses combined. So this block will be 2 plus 5, which is 7 kilograms, okay? So it combines both masses, 7 kilograms. Right, so I don't really recommend this method unless you have practiced enough. And then what you do is, because you ignore the tension of the string, it means you only take the other forces that remain. So you'll have the weight, right? You'll have the kinetic friction opposing, and then I think we had the weight parallel here. You'll have the weight parallel. I won't write it explicitly because there's a bit of caveat to this method. So, and then you have, yes, the weight of the overall object. Then from here, you can say Fnet is equal to ma, and you only consider 1, 2, 3 forces, right? So that is essentially how it works. And then, yes, but Try it. You can check our other video where I did it extensively, and then try it and see if you can get the same answer as with this method we just use here. Right, so this method works it works all the time. It's just sometimes it can be tedious. So method 2 is for people that like taking shortcuts but still get to the same answer. Right, so just use this and let me know what you get. Okay, with that being said, this is the end. Is it the end? Let's check. Oh yes, so we're left with 3.6. all right, sorry, let's handle 3.6. We are asked to calculate the tension in the string between the two blocks. That's an easy task now. So we have two equations. We have 1, we have 2, and they are all describing tension between the in the string between the two blocks. So you can choose whichever equation you like. I like equation 1, so I can use equation 1. You can say this is 3.6, and my equation 1 was saying T is simply 2A. T was simply 2A plus 14.89. And we just found that our A is 4.87. Therefore, we can substitute it here. Say 4.87 plus 14.89. This gives us, I get 24.63 newtons. All right, so that's what I get, 24.63 newtons. So yes, this is now the end of our video. So yes, thank you very much. We will catch you on our next video. Bye for now.